What is the most efficient way of finding all the factors of a number in Python? Can someone explain to me an efficient way of finding all the factors of a number in Python 2.7? I can create an algorithm to do this, but I think it is poorly coded and takes too long to produce a result for a large number.
This will return all of the factors, very quickly, of a number n. Y square root is the upper limit. sqrt(x) equals x. So if the two factors are the same, they're both the square root. If you make one factor bigger, you have to make the other factor smaller. This means that one of the two will always be less than or equal to sqrt(x), so you only have to search up to that point to find one of the two matching factors. You can then use x, fact1 to get fact2. The reduce list _@_, is taking the little lists of fact1, fact2, and joining them together in one long list. The I in /I, for I in range 1, and sqrt(n) plus 1, if n%i == 0 returns a pair of factors if the remainder when you divide n by the smaller one is 0. It doesn't need to check the larger one too, it just gets it by dividing n by the smaller one. The set ... on the outside is getting rid of duplicates, which only happens for perfect squares. For n equals 4, this will return 2 twice, so set gets rid of one of them.
The solution presented by @agv is great, but one can achieve 50% faster runtime for an arbitrary odd number by checking for parity. As the factors of an odd number always are odd themselves, it is not necessary to check these when dealing with odd numbers. I've just started solving Project Euler puzzles myself. In some problems, a divisor check is called inside two nested for loops, and the performance of this function is thus essential. Combining this fact with agv's excellent solution, I've ended up with this function. However, on small numbers, tilde is lower than 100. The extra overhead from this alteration may cause the function to take longer. I ran some tests in order to check the speed. Below is the code used. To produce the different plots, I altered the x equals range 1, 100, 1 accordingly. No significant difference here, but with bigger numbers, the advantage is obvious.
Agv's answer is really quite cool. I wanted to see if I could rewrite it to avoid using reduce. This is what I came up with. I also tried a version that uses tricky generator functions. I timed it by computing. I ran it once to let Python compile it, then ran it under the time1 command 3 times and kept the best time. Reduced version, 11.58 seconds, tools version, 11.49 seconds, tricky version, 11.12 seconds. Note that the ATTools version is building a tuple and passing it to flatten_eta. If I change the code to build a list instead, it slows down slightly. ATTools, list, version, 11.62 seconds. I believe that the tricky generator functions version is the fastest possible in Python. But it's not really much faster than the reduce version, roughly 4% faster based on my measurements.
There is an industry-strength algorithm in SymPy called factorization. This took under a minute. It switches among a cocktail of methods. See the documentation linked above. Given all the prime factors, all other factors can be built easily. Note that even if the accepted answer was allowed to run for long enough, i.e. an eternity, to factor the above number, for some large numbers it will fail, such the following example. This is due to the sloppy in n0.5. For example, when n equals 10 quadrillion 79 we have. Since 10 quadrillion 79 is a prime, the accepted answers algorithm will never find this factor. Note that it's not just an off by 1. For larger numbers it will be off by more. For this reason it's better to avoid floating point numbers in algorithms of this sort.
If you want to see more, please consider subscribing.